Hello everyone. In this video we are going to talk about branch. Okay, so last video, if you remember, we talked about something called a branch, right? So now we are going to talk about a branch of a multivalued function f. Multivalued function. Okay, so what does it mean? So first of all, what is a multivalued function? Of course, you know that generally speaking in R, the functions which we deal with are single valued, right? So but here, as you can see, for example, we have seen log, right? Log z. Huh? So what is it? It is basically the real log of mod z plus I times the argument of z, right? And since argument of z, this is by itself a multivalued function, because you know you have to, this 2 and pi thing is there, right? So it's a multivalued function. So actually that turns the log into a multivalued function. Okay, but the thing is, generally speaking, it is not a very good practice to work with multivalued function, because the thing is you don't know which value it is actually taking. Okay, so we want to put it like a single valued function. We want to look at it as a single valued function. So what is it? See, so then we define something called a branch. Okay, so let me define. So this is definition. A branch of a multivalued function. A branch of a multivalued function. Okay, and let's just call it f. So think of it as your log function. Okay, so this is any single valued. So this is any. So there are many valued part, right? So I'm just looking at the single valued one. Single valued function. Okay, f, capital F, we'll call it a capital F. That is analytic. Very important. By definition is analytic. That is analytic in some domain. Okay, let's just call at each point z. Okay, of which f of z is one of the values of small f. Clear? So see, think of it like this. Let's say fz equals to log z, right? Log of z. Now if you want to write it properly, that will have that this is log of mod z plus I times argument of z, right? Okay, so if you just think about it this way, there is, for n equals to 0, for a particular z naught, let's say, this will give you one value, right? So you see, that is one branch, because if you restrict it between minus pi and argument of z and pi, okay, if you restrict this part, okay, so essentially I am taking the principal part, that is, if you do that, then you have a single valued function, and for every z naught you get just one value out of it. And then if you take this principal argument and add another 2 pi with that, then that will give you another value, right? So essentially what is happening is this is a single valued function. We are talking about a single valued function, capital F, okay, which has to be analytic, where in some domain where f of z is one of the values of capital F. Okay, so let me give you a proper example with this log. Let me just write it down. So example, you see, if you take, let's say, log of z, the principal log of z, what is it? This is nothing but the real log of r is mod z, plus I times theta, right? Okay, and what is r? R equals to mod z, which is greater than 0. This is by definition, we already know. And what is theta? Theta is the argument which we are going to define it between minus pi and pi. Clear? Okay, so please note, theta is between minus pi and pi. Okay, so this is a branch. Of course, this is a branch of the logarithm, because it is one single valued function, and we know that in this part it is going to be analytic, right? We know that. So okay, so this is a branch. So we call it a principal branch of log. Principal branch. Okay. Now We will also define something called a branch cut. Branch cut. So what is a branch cut? Let's just understand this thing. See, a branch cut. So a branch cut is a portion of a line or a curve Okay, I will give you an example that is introduced in order to define a branch, define a branch capital F, okay, of a multivalued function small f, of a multivalued function small f, okay, small f. Okay, so you see, if you look at the points of the branch cut, okay, so think of it like log, huh? You see, this is your log, this line, along with the origin. Yeah, so what is it? You see, if you take a point on here, okay, those points, log is not analytic. Here it is not even defined. So those points, we will call it a singular point. So essentially, points of the branch cut for f are singular points of f. I hope this is clear. We showed that the function logarithm is not defined here, right? It's not defined in this point, and of course at 0. So sorry, not defined, is not continuous or analytic at this point, and it is not defined at 0. So those points we'll call it as a singular point of f. Okay. So in this case, this is log of z. Okay, and so example, you see the origin and theta equals to pi is a branch cut of f z equals to log z. Now you have to specify which log are you talking about. See, here you are talking about the argument will be between minus pi, argument of z between pi and minus pi. With that particular log, this is a branch cut. Okay, this is the branch cut. See, you can change this logarithm. So basically the whole definition can be changed. You can think of it like this. See, note. See, here I took theta to be 0. So you can take any. So essentially, without this also, you can take this to be your branch cut. Theta equals to alpha. In this case, I mean, it will start from here. Okay, so essentially in that case you can also define, so we can actually change the definition. Log of z, we can define it to be log of mod r plus I times theta. This theta is the argument, right? This argument we can change. So basically r will be greater than 0 and alpha. So theta will lie between alpha and alpha plus 2 pi. You can do that also. Clear? So for every real number alpha, this every alpha is any real. Alpha equals to 0 will give us this, or otherwise this. See, here what is happening is this. So let's say this is your alpha. Let's just take this is your alpha. So basically theta between alpha and alpha plus 2 pi. So alpha plus 2 pi. Okay, so within this particular thing, so it will start from here. It's not starting from minus pi. It's not starting from minus pi, not starting from here. So essentially from here to theta plus 2 pi, and then you can have another logarithm also, and then you can also define it like this particular another branch cut. So in that case the branch cut will be theta equals to alpha plus pi. Okay, right. So So question, find the branch cut for this logarithm. Find the branch cut for this definition. Okay, for this definition means this definition. Clear? Okay. So in this case, what is the branch cut? In that case, it will be theta equals to alpha. Please write theta equals to alpha. You please check from this part. That will be a branch cut in this case. Okay, right. So now let's just look at one example. So it is very important that you look at a proper branch which you are talking about, because there are many properties of logarithm which are not, defined here. See, let's say if we define something like this. The principal log of I cube, let's just find it. Okay, what is it? This is the principal log of I cube is minus I, right? So what is it? It is the real log of mod minus I, which is 1. So log 1 is 0. I times, you see, minus I. Okay, if you look at it, minus I. Okay, so it will be minus I right here. So essentially it is minus pi by 2. So minus pi by 2 plus I times argument, which is minus pi by 2. So this is nothing but minus pi by 2 times I. Okay. Now if you, so we know from real variable that log of a to the power n is nothing but n log of a. Of course a is positive, We're assuming all that. From real we know this is happening, right? So here what is happening here? Okay, let's just look at it. What about 3, the principal log of I? Let's just look at it. See, 3 times, what is principal log of I? It is nothing but log of mod I, which is 1, log of 1 is 0, and then plus I times I. So I is here, so the argument is going to be pi by 2. So it is I times pi by 2. So it is nothing but 3 pi by 2 times I. See? So you see, in this case, log of I cube is not equals to 3 capital log of I. Okay. So when you are assuming that this argument lies between minus pi, argument of z, and pi. Yeah. With this is not true. Yeah. So please keep that in mind. Okay. So what I am trying to say is this: depending on branches, the properties of logarithm changes. Don't just assume it like this. So essentially, with our usual logarithm definition, which we take the argument between minus pi and pi, log of I power n is not going to be n I log of I. Clear? Okay. Again, so A, B. This I want you to check. I'm not going to do it, but let's say if you are assuming R positive, of course, and theta to be pi by 4 theta and 9 pi by 4. You can take that also as your argument. You can change that. And if you do that, so basically your, here log of z will be defined as log of r, which is mod z, plus I times, okay, theta. And theta lies between here. If you do that log, then you can actually check that log of I square is going to be 2 times log of I. Okay, so you see, in that case it is defined. So please make sure that you know which branch of logarithm you are working with. Depending on the branch, the properties change. Yeah. Okay, so please keep that in mind. So essentially what I'm trying to say is this: see, small log, let's say, of I square. Yeah, this has a set of values, right? That set may not be equals to 2 log I. Yeah, 2 log I, depending on whatever argument you are choosing. So basically this is a multi-valued function, right? So things are very, very complicated here. We don't want that complication in life. That is why we are taking it to be a particular definition, and based on that we are taking a particular branch of that function. I hope this is clear. Okay, so that is about logarithm. And of course you can also define the a power a power z function also exactly like this. That is also a multi-valued function, and you can talk about branches of that function. Okay, so we are going to end this particular week with this particular section, which is the inverse map. Okay, so we talked about sine, cosine, you remember. Now we'll talk about the inverse trigonometric functions. Okay, so inverse trigonometric functions. trigonometric functions. Okay, let's just see. The thing is this, we want to define sine inverse of z. That's what the idea is. Okay, so you see, let's write w equals to sine inverse of z. Sine inverse of z. Z is given to be in C. So we are assuming that there is a w in C such that we can calculate what sine inverse of z is. So if that is the case, then of course sine of w is going to be z. Okay, which is given to us, z is given to us. Yeah, we want to find how w looks like. Okay, so if that is the case, therefore so what does that mean? That is that w equals to sine inverse of z. What does that mean? It means that z, this is sine of w, right? What is sine of w? You remember we talked about sine. It is e power iw minus e power minus iw by 2i. Okay, of course you can also do the exact same thing for cosine. I am not going to do the cosine part. I am just looking at the sine part. Yes. Okay, so if that is the case, then you see this, what do we know? We know what z is. We have to find what w is. We want to express w in terms of z, right? Okay, so in that case what happens is you can just write everything down. Therefore we actually end up with the equation. How does it look like? E power iw square minus 2i z, it is given to us e power iw, okay, minus 1, this is equals to 0. This is what we actually end up with. Okay, and you do clearly realize that that's a quadratic function. You can solve for e power iw. If you solve it, so please check this part. One second. Yeah, check this part. That solving for e power iw, what do you get? You get e power iw. It's a quadratic, right? So it will give you iz plus 1 minus z square whole power half. Okay, and you see here 1 minus z power whole power half, this particular function. Yeah, so note 1 minus z square whole power half, this function, this is again a multi-valued a double valued function, right? Is a double valued function of z, valued function of z. Yes. Okay, so if you take logarithm on both sides, so basically e power iw is this, right? So I want to write down as w. So if you take the logarithm on both sides, what do you get? You get that iw, if you take the logarithm here, you get iw is I. What is w? W is sine inverse z, right? So you get sine inverse z equals to 1 by I, okay, which is minus I, and then the logarithm of this particular term, which is the log of I z plus 1 minus z square whole power half. Yes, I hope this is clear. Okay, so you see what we are actually getting is, note again, A, B, what we are getting is sine inverse z. Sine inverse z is a multi-valued function. Okay, what about sine? Is it a multi-valued function? No, but sine inverse z, yes, it is multi-valued function. And how many values are there? See, since log is infinitely valued, sine inverse z is also going to be infinitely valued. Okay, and is infinitely valued. So here also, if you want, since this is concerning log, you can also talk about the branches and all. Okay, so let me give you an example to clarify all of this. So how do you calculate some stuff like that? Let's say a very simple example is sine inverse of, let's say, minus I. Yeah, very simple example. So what is this thing? Yeah, okay, so you see, first of all, z here z is minus I. We just put it in the formula if you want. Okay, so let's just do that. So you see, you have to calculate log of iz plus 1 minus z square whole power half. So basically log of iz, z is minus I, so it is minus I square, which is 1. And then the other part is 1 minus z square, so 1 minus, this is root 2, right? Okay, root 2. So log of 1 plus root 2. So what is it? it is essentially, so this is, please remember this thing, yeah, very, very important. See, this is of course a real number, okay, but the thing is we are looking at it from the complex lens, okay. So this is real part of 1 plus root 2, and then you have 2n pi I, yeah, because here the imaginary part is 0, okay. So it is 2n pi I, okay, and this is n equals to 0 plus minus 1 plus minus 2 and goes on. So essentially you see, when n equals to 0, this actually coincides with your real logarithm, okay. So please keep that in mind, that log of 1 plus root z is nothing but this, okay. And log of 1 minus root 2 similarly is going to be log of 1 minus root 2 plus 2n plus 1 pi times I, okay. Again this is n equals to 0 plus minus 1, so basically all the integers, okay. So see, since log of root 2 minus 1, okay, this is nothing but minus log of 1 plus root 2, okay, then you see all this you can actually put it, therefore sine inverse of minus I, you can just write it as n pi, okay, plus I times, please check this part, minus 1 whole power n plus 1, and then log of 1 plus root 2. If you put everything together, it will look like this, okay, and of course n is in z, okay. So you see, this is how you calculate what sine inverse of z is, yeah. And one very, very important here to understand this thing is, see, even this number, see this number, even though this is a real number, what happens is you actually end up getting, you know, complex parts. So essentially for n equals to 0 you get the real thing, but again you also have that complex parts, okay. So please keep that in mind when you are calculating complex logarithm, because this is a complex logarithm we are talking about. There are real, so even real numbers, if you take the complex logarithm, you are going to end up with a complex part, okay, right. And similarly, so please check this part, similarly you can also find that cosine inverse z, so you have to check this part, exactly the similar sort of thing what you do, this you can find, it is minus I logarithm of z plus I 1 minus z square whole power half, okay, and tan inverse of z is equals to I by 2 and then logarithm of I plus z by I minus z, okay. This is very important that you actually see how these two can be derived, okay. Right, I will write down some formulas which I want you to, at least check, okay. So check this part, check, okay. So if you take the derivative of sine inverse of z, of course where you are just looking at one of the branches, it's not like that. So it is 1 by 1 minus z square whole power half, okay. And again, if you are taking cosine inverse z, the derivative of it, it is minus 1 by 1 minus z square whole power half, okay. And the derivative of tan inverse of z is going to be 1 plus 1 plus z square, which you expect, okay, right. So with this, I mean, we have a very good pretty idea about what exactly is the inverse function, okay. Now with that thing in mind, I just want you to check another part, that check this part also, that what is sine hyperbolic inverse of z, check this part, and it is going to be log of z plus 1 plus z square whole to the power half, okay. And similarly cosine and tan you can actually define. So I think you have a pretty good idea now what inverse function is. Please remember, it is a infinitely valued function, okay. So with this I am going to end today's video. Thank you.